Hello and welcome to our ICRA 2020 presentation. My name is Maciej Bednarczyk and I will give you an insight into our work entitled Model Predictive Impedance Control. Contrary to traditional robotics, where all unexpected interactions are prohibited, in modern robotics, interactions between the robot, their environment, and human operators are not only allowed but also desired. Dealing with interactions opened many research areas leading to the development of dedicated robotic solutions such as collaborative robots or cobots, but also specification of safety requirements and a high interest in interaction control strategies. At this time, one of the hot challenges, and the one addressed in our work, consists in designing robot controllers that allow to obtain a prescribed compliant behavior while respecting a set of practical robotic constraints. Constraints can range from position limits that stop the robot from entering a specific area of the workspace to velocity and force limits that prevent injuries. Adding constraints is a way of ensuring security during human-robot interactions. To start, we focus on one of the most popular interaction control strategies, which is impedance control. First, let's consider our robotic system dynamics to be linearized to a double integrator in task space by the mean of computed torque control and the robot kinematic model. The goal of impedance control is to substitute the robot dynamic behavior with an impedance model described by its virtual inertia, stiffness, and damping in response to some external forces. This can be achieved by applying the following input to the system. Impedance control is of particular interest for interaction control, as it can simultaneously deal with contact forces and motion control, and also shows advantageous stability properties as well as a high customization of the parameters. In contrary, in its classical version, imposing constraints becomes challenging and no anticipation is possible. Another interesting feature of impedance control appears when expressing the linearized dynamics and the input leading to the desired impedance model in state space. In this case, impedance control becomes a classical form of state feedback control described by its gain k and tracking some reference trajectory. The state feedback gain k depends on the impedance parameters such as the virtual inertia, stiffness, and damping. In order to deal with constraint systems, a popular control strategy is model predictive control. Model predictive control deals with complex multivariable constraint control problems by solving optimal problems online. It consists of a model-based optimizer to which a cost function is given subject to a planned model, some set points and constraints on input at states. The model predictive controller then measures at each step the system current states and outputs and uses the model to predict future evolutions of the system. This allows to compute the next optimal input such that the system respects the given constraints. Our goal is to design a controller that combines both features of model predictive control and impedance control. To do so, we focus on the state feedback representation of impedance control and use it to design a zero-value cost function for model predictive control. This cost function makes the tracking of the desired controller as the primary objective. In fact, one can notice that if the output UK is equal to the desired control scheme, the cost function is equal to 0. Using this cost function, a classical model predictive control problem can be formulated subject to the system dynamic model. The model predictive control weights are expressed in function of the state feedback gain K. In order to better deal with fast input changes, we introduce the input rate of change into our MPC problem. The resulting model predictive control problem can be formulated as a quadratic problem. Additional constraints can be included at this time. It is worth noticing that in the case where no other constraints are active beside the system model, the quadratic program has an analytical solution which, as expected, is equal to the desired impedance state feedback. We tested our controller on the experimental setup featuring a KUKA Iowa cobot following a smooth trajectory in task space. On the path of the robot and effector, we placed an obstacle. An external force torque sensor mounted on the robot flange is used to measure external forces. The robot is torque controlled and the commands are sent via the KUKA FRI interface. In this first experiment, we were interested in comparing the performance of impedance control with model predictive impedance control without constraints. The presented graphs give you the end effector trajectory, Cartesian velocity and acceleration of both impedance control and model predictive impedance control, as well as the followed reference. As we can see, there is an almost perfect matching between the two controllers, with a mean error of less than 0.25 mm and a standard deviation of less than 1.5 mm. It is also worth noticing that both controllers react the same way to the unmodeled interaction caused by the obstacle. We also observe that the reference tracking performance is not ideal, which is caused by the low stiffness and the robot low-level control. For this reason, we were interested in quantifying the impact of the impedance model. We show that the impedance model maximum error on the virtual inertia is of 8% and for stiffness and damping of approximately 6%, which is acceptable as such differences are not perceptible when interacting with humans. The second experiment adds constraints into MPIC. First, we added position constraints that restrict the end effector trajectory to some allowed area. As we can see, model predictive impedance control behaves as the same as impedance control in the allowed area, however diverges from IC at the boundary in order to respect the constraint. A similar result can be observed when adding constraints on the velocity. Finally, it is also possible to add constraints on the input generated by the controller. It is worth noticing that when limiting the input, the forces generated by the end effector on the obstacle are also limited. In the last experiment, the constraints are added in order to restrict the allowed area of the end effector trajectory. In addition to the previous validation, interactions are not only due to the obstacle placed on the path, but also human-robot interactions. As we can see, the controller makes the end effector compliant to these interactions, but does not allow to get outside of the restricted area, even if pushed against the boundary. To conclude, we saw that impedance control had great advantages when dealing with contact forces and motion control, and also had interesting properties in terms of stability and customization. However, it does not allow to deal with constraints and prediction. We showed that it is possible to combine impedance control with model predictive control, resulting in our model predictive impedance control that can address these issues and by such increase security for human-robot interactions. In order to extend the presented method, future work aims at providing theoretical stability of model predictive impedance control when constrained, as well as adapting the impedance parameters online and being able to assess human activity to fully profit from the anticipation features of model predictive impedance control. Thank you for your attention, and I'm looking forward to answer all your questions and discuss our methods soon on the forum.